first we need to find the work done by Earth when a mass is thrown downwards on a spring. To do that, we need this formula: force times change in position is equal to the work done by the Earth, and that can be rewritten as the force of mass times gravity multiplied by the change in direction, which is just the height, or the y direction. X and z isn't relevant right now. We have to convert our mass into kilograms, which is right here, and we plug in our numbers: the mass, speed of gravity, or acceleration done by gravity, and the position change, which is negative 0.08, and we get our final answer of 0.075 joules. Next, we want to find the work done by the spring, and we start with the fundamental energy principle, and this can be broken down into the work of the Earth plus the work of the spring is equal to the final energy minus the initial, which would be the change in energy. The rest energies are the same, so they're cancelled, and the spring tends to decrease kinetic energy, so we're not using potential energy here. And we're left with work of the Earth, which we know, plus the work of the spring, which we want to find, is equal to the two kinetic energies, final minus initial. Those are rewritten, broken down more, into half of the mass times the velocity squared minus the final minus initial. And once we plug in all these values, which we're given, we find that the work done by the spring is negative 0.943 joules. First, we're asked to find the velocity of the ball after it leaves our hand. I worked it out right here, but this isn't a very good explanation of how I got my answer. A better one is rewritten here. We can use the momentum principle because we're given time, and it's just an easier formula to work with if we have the variables needed to do so. F net, the only force acting on it is the force of gravity, so we have the mass times the negative acceleration due to gravity is equal to change in momentum over change in time, which is rewritten as the mass times the final velocity minus initial velocity. For this part, I chose the final velocity to be where the ball is at the crest or peak, because the velocity is 0. So now we're just working with the mass times the velocity initial, which is what we're trying to find, and it's negative. So negative mass times velocity initial over delta t is equal to the negative force. We multiply this time by the force, and we divide by the negative mass to get a positive 12.3 meters per second. Next, we're asked to find the maximum height that the ball reaches. The work energy principle can be broken down into the final potential energy is equal to the change in kinetic energy, which is convenient because h is the variable that we're looking for. We can plug in all the known values, which is the mass and the gravity, as well as the final velocity that you choose to be 0, which makes it better because it cancels this whole value out, minus the initial velocity, which we found up here. After plugging everything in, we find that the maximum height the ball can reach is 7.71 meters.